Let us now talk about the entropy principle. Now, for any infinitesimal process that a system undergoes, we know that ds, that is the entropy change, is greater than or equal to dq upon t. So this is a very famous inequation that we have come across in our previous videos. Now, for an isolated system which does not undergo any energy interaction with the surroundings, okay, so for an isolated system, so we are talking about the entropy change for an isolated system, okay, so you would have dq is equal to 0, isn't it? So this means that ds for an isolated system is greater than or equal to 0. So this is a very important thing to understand. Alright, so let us name this equation 1. Now, if you talk about a reversible process, for a reversible process, now we know that for a reversible process the entropy change is 0. This means that the entropy value is a constant value. So this is for the reversible process. And for an, or you can say for an irreversible process, for an irreversible process, the value of entropy change is greater than 0. Okay, so we have three things. This is the second equation and this is the third equation. Now it is thus proved that the entropy of an isolated system can never decrease. Okay, so I can also say that this is an isolated reversible process or a isolated reversible system, and this can also be for an isolated irreversible system. Okay, so if you combine equation 1, equation 2 and equation 3, you can say that the entropy of an isolated system can never decrease and it will always increase and remain constant only when the process is reversible or irreversible. Okay, so if I write it down, it says that the entropy of an isolated system can never decrease, alright, it will be equal to 0 or positive depending on whether the process is reversible or irreversible, and this statement is called the entropy principle. Okay, and this statement is known as the entropy principle. So you should note it down. It is very, very important for us to understand. Okay. Now, how do you make a system isolated? So you can say that an isolated system can always be formed by including any system and its surroundings within a single boundary. So if I have to create a diagram for it, okay, so this is a system. So the system has some work and heat interactions with the surroundings. All right, now I include this system within another boundary. So this is the boundary of the system, isn't it? So I create another boundary around it. Okay, so this is the system and this is, you can say, a boundary which is engulfing this system. So this main system, or you can say the original system, is then called a subsystem. Okay, so this is called the subsystem, or you can say the original system, and now we can say that this system has now become an isolated system. Okay, so this is how you make a system isolated, that is by including this into another boundary, and thus making it a subsystem. Now, the system and the surroundings together, it is called a universe. We know this. Okay, so I can say that the entropy change of the universe will always be greater than or equal to 0. Now we know that the universe means the entropy change of a system plus the entropy change in a surroundings. So these two things added up give you this equation. So let us say this is equation number 4. Okay, now a very important thing that we should understand, that entropy may decrease locally at some region within the isolated system. So we just the entropy principle stated that the entropy of an isolated system will never decrease, but it might decrease locally at some region within the isolated system, but it must be compensated by a greater increase in entropy somewhere within the system, so that the net effect of any irreversible process is an entropy increase of the whole system. Let me make you understand this in an easier way. So I hope you have understood the statement. If not, listen to it again by going back in your video players. So this is what it is. So let us say this is my system, an isolated one. Now I said that the isolated system entropy can never decrease. It will always be greater than or equal to 0. Let us say at this point, now this is within the system, at this point the entropy decreases due to some irreversibility which you can't control. Now if this happens at some place else within the system, the entropy should increase, so that the net effect of the for the complete system stays positive. Okay, so this is how you can check for the irreversibility. So this means the entropy increase of an isolated system is a measure of the extent of irreversibility of the process that the system undergoes. Okay, so if this is a small irreversibility, the entropy increase elsewhere would have to be not much. But if this irreversibility is of higher extent, then the entropy decrease would be very high. So to compensate for that decrease, this increment elsewhere has to be very high. So if you are getting this a very high value, then you can say that the irreversibility within the process is very, very high. Okay, so I'll write it down, this statement also, that you can also note it down, the entropy increase of an isolated system is a measure of the extent, is a measure of the extent of reversibility of the process, or of the irreversibility of the process. Extent of irreversibility of the process. You should note it down, and I hope this is clear to you now. Okay, now if you draw a diagram, let me draw a diagram. Okay, so this is between the entropy of an isolated system. So this is the entropy of an isolated system, and this is x, which shows any state of the system, any random state. Okay, now the entropy of an isolated system always increases. So when the state changes, the system undergoes a process. So let us say from this state you are changing the state of the system, and the entropy starts to increase. Okay, and it becomes a maximum value at the state of equilibrium. So let us say this is how. So this is the maximum value. at this maximum value, I would say that the state achieved is a state of equilibrium, XE. Okay, and it will stay the same. So there will be no increment in the entropy of the system after this. So this is S isolated maximum. Alright, so this is how you can look at this entropy increase with the state change. So this is the equilibrium state. This is the equilibrium state. Okay, so we can say that when the system is at equilibrium, in the other way around, any change in the entropy would be 0, because you have the maximum entropy over here and it's a straight line after that. Okay, so you can say at equilibrium state, okay, the entropy change in an isolated system is 0, because this is a constant entropy. Okay, so this is all that we have to cover in this topic of entropy principle. I hope you understood the key concepts, that is the definition of the entropy principle and the entropy change of an isolated system. Okay, so these are the some points that you need to understand and remember. And thus the entropy increase of an isolated system is a measure of the extent of irreversibility of the process, and this, that is at equilibrium state, the entropy changes are 0. So it will be very good if you are able to remember this diagram as well, which indicates or which quantifies or represents the entropy of an isolated system and the state change. Okay, so this is all that we have to do in this video. In the next video, we start with the applications of the entropy principle on various processes.